By 1989, the Voyager 2 spacecraft was an elder of the solar system. 12 years past its launch, its systems aging, its instruments weary from the cold and radiation of deep space. Yet it still pressed onward, following a trajectory that would take it to the farthest known planet. Its mission had begun with Jupiter and Saturn, continued through Uranus, and now, beyond 4 billion kilometers from the Sun, it was about to complete its final planetary encounter, a meeting with Neptune, the last great giant of the solar system, and the cold frontier of the Sun's dominion. For the scientists and engineers who had guided Voyager since 1977, this was both a scientific milestone and an emotional farewell. No spacecraft had ever visited Neptune, and none would again for decades. When Voyager 2 arrived, it would not just reveal a new world, it would close an era. Humanity's first grand tour of the planets was ending. Neptune had always been an enigma. Discovered in 1846 not by sight, but by mathematics, it was the first planet found through calculation. Its existence predicted by irregularities in Uranus's orbit. Astronomers Leverrier and Adams had inferred its presence before any telescope had seen it. To many, that discovery marked a triumph of human intellect over cosmic mystery. But for 143 years afterward, Neptune remained a remote blue point, barely visible even in the best telescopes, a world known only by its pull on others. Voyager 2 changed that. As it approached in the summer of 1989, its cameras began to resolve a shimmering sapphire disk. The closer it came, the more alive the planet appeared. By August, scientists could see streaks of cloud bands, faint rings, and an enormous dark oval, a storm system later named the Great Dark Spot. It was the first time humanity had seen Neptune's true face, a deep cobalt world swirling with motion, vibrant and wild, nothing like the calm of Uranus. On August 25, 1989, Voyager 2 swept past Neptune at a distance of 4,950 kilometers above the cloud tops, closer than any previous planetary encounter. In that moment, the spacecraft's cameras captured images so crisp that they revealed details only 50 kilometers wide. Astonishing resolution for a planet 4 billion kilometers away. Every instrument was alive: magnetometers, spectrometers, radio receivers, plasma detectors, all focused on decoding a planet no one had ever touched or seen up close. The data poured in. Neptune's atmosphere, dominated by hydrogen, helium, and methane, glowed in a shade of blue, unlike any other planet, richer and deeper than Uranus's pale turquoise. Methane absorbed red light, leaving only azure and violet, but the intensity of the color suggested something more. Perhaps trace hydrocarbons or unknown chromophores that tinted the clouds with their own spectral fingerprints. Voyager's instruments found that Neptune's cloud tops hovered near 218 degrees, yet beneath the frigid calm, fierce winds howled, the fastest in the solar system, reaching speeds of 200 kilometers per hour. Even in the dim sunlight, Neptune's atmosphere churned with energy as though powered by an internal engine. The spacecraft discovered a second storm, the small dark spot, another colossal vortex, and a white feature dubbed Scooter, racing around the equator faster than any known cloud formation. These were not static ancient storms like Jupiter's Great Red Spot. They were living tempests, shifting and reforming in weeks. Neptune, far from being inert, was a planet in constant motion, a paradox of distance and dynamism. Voyager's instruments revealed that Neptune radiates 2.6 times more heat than it receives from the Sun, a discovery that astonished scientists. Somehow, the coldest planet in the solar system possessed a hidden furnace. Theories emerged: leftover heat from formation, slow gravitational contraction, or convection in the deep mantle of water, ammonia, and methane ice. Whatever the source, it powered the jet streams and storms that whipped across the planet, feeding the blue maelstroms that Voyager watched unfold. The planet's magnetic field proved just as strange as Uranus's, tilted by 47 degrees from the rotation axis and offset by more than half the planet's radius. The result was a magnetosphere that twisted and flipped every rotation, sweeping the solar wind into spiraling arcs. Voyager 2 detected bursts of radio emissions and auroral activity, faint echoes of electrical storms dancing across the poles. Neptune's magnetism, though chaotic, was powerful, its field strength comparable to Earth's despite the planet's immense size. Then came another revelation: Neptune's rings. For decades, astronomers had suspected their existence due to occasional dips in starlight, but Voyager confirmed them at last. 5 narrow, dusty rings encircling the planet, each distinct and dark, made of ice-coated in radiation-darkened material. Most striking were the ring arcs, bright, uneven clumps that defied gravity. Scientists had expected the rings to be smooth, but instead, they appeared fragmented, as if some unseen hand were gathering the particles into luminous knots. Later analysis revealed the cause: small shepherd moons, such as Galatea and Despina, whose gravity corralled the ring particles into arcs. The result was a living ring system, sustained by resonance and motion, precariously balanced at the edge of chaos. Voyager's cameras also discovered 6 new moons, bringing Neptune's total to 8. Among them were Proteus, a large, irregular body dark as asphalt, and smaller satellites orbiting in close proximity to the rings. But the most captivating target was still to come: Triton, Neptune's largest moon, a frozen world orbiting backward against the planet's rotation and destined one day to spiral inward and shatter into a new ring system. Voyager's trajectory had been carefully planned to pass within 40,000 kilometers of Triton, a close encounter that would make it one of the most important discoveries in planetary exploration. As Voyager 2 sped past the planet, it looked back and captured a haunting sequence of images. The crescent of Neptune, half in shadow, gleamed like a distant ocean world suspended in darkness. Beyond it, faint stars glimmered against the abyss. For the mission team, these were more than scientific images. They were farewells. This was the final planetary encounter of the 20th century, the end of a journey that had begun with the optimism of the 1970s and spanned the technological limits of human ingenuity. At Mission Control in Pasadena, the data arrived in real time, taking 4 hours to cross the gulf between worlds. The final confirmation: Voyager 2 has flown past Neptune, was met not with cheers, but with silence, followed by applause tinged with awe. For some of the scientists, it was the culmination of their careers. "It's like saying goodbye to a friend," one engineer whispered as the final frames came through. Voyager 2's encounter with Neptune lasted only a few days, but it transformed everything we knew about the outer solar system. It revealed a world of motion, energy, and color, a dynamic twin to Uranus, but alive in ways no one had imagined. It proved that even at the edge of sunlight, Planets can pulse with internal heat and storm with fury. And in its wake, it left behind questions that still echo today. Why is Neptune so active? What fuels its winds? What drives its magnetic chaos and thermal glow? In the years that followed, Hubble and ground-based observatories would track Neptune's ever-changing atmosphere. The Great Dark Spot, Voyager's signature image, vanished within a decade, replaced by new storms in the opposite hemisphere. The planet continues to evolve, shifting and reshaping itself in cycles we are only beginning to understand. Each new observation deepens the mystery rather than resolves it. Neptune remains the most remote of the planets, still whispering across the void, alive, distant, and defiant of its cold surroundings. Voyager 2's passage past Neptune marked the end of an age. After the encounter, the spacecraft's cameras were turned off forever to save power. Its final planetary photographs included one last haunting image, Neptune's crescent fading into darkness, and beyond it, the faint glint of Triton, orbiting against the flow, its icy face reflecting the blue of its master planet. The journey that had begun at Jupiter's swirling storms had now reached the frontier of the sun's warmth. Everything beyond lay in interstellar night. In the decades since, Voyager 2 has continued outward, carrying its golden record of sounds and music from Earth, a time capsule for whatever intelligence might one day find it. But for those who watched its final planetary encounter, Neptune remains a symbol of distance, of endurance, and of the human need to keep going, even when the light grows faint. The stormy blue world that Voyager revealed in 1989 stands as a monument to the farthest reach of our mechanical eyes, a place where the sun is only a star among stars, and yet where motion, energy, and beauty endure. For all the coldness of its realm, Neptune burns with vitality, a living proof that even at the edge of the solar system, the fire of creation still glows. To look upon Neptune is to glimpse motion incarnate. At first glance, its deep blue disk seems calm, a serene ocean of methane clouds turning slowly at the edge of the solar system. But beneath that placid hue lies one of the most violent atmospheres in the cosmos. Voyager 2's brief encounter in 1989 revealed a world where winds rage faster than any hurricane on Earth, where storms the size of continents form and vanish within years, and where, against all logic, the coldest planet burns with internal heat that refuses to die. The story begins with a contradiction. At nearly 4.5 billion kilometers from the Sun, Neptune receives less than 1,000th of the sunlight Earth does. Its surface temperature hovers around 220 degrees, cold enough to freeze methane solid. Logic dictates that such a world should be still, a frozen, inert sphere drifting in darkness. Yet Voyager 2 found the opposite, a planet alive with motion, turbulence, and storms so immense that they could swallow the entire Earth. The greatest of these was the Great Dark Spot, a vast, oval-shaped storm system nearly the size of our planet. In Voyager's images, it appeared as a deep shadow encircled by bright white clouds, high-altitude methane ice crystals whipped into spirals by supersonic winds. This was not a solid feature, but a roaring vortex, an anticyclone similar in nature to Jupiter's Great Red Spot, yet far more dynamic. Its winds screamed at more than 1,200 kilometers per hour, the fastest ever recorded on any planet. To scientists accustomed to the sluggish air of Uranus, Neptune's ferocity was staggering. How could such a distant world generate so much energy? The answer, Voyager hinted, lies beneath the clouds. Unlike Uranus, Neptune radiates more than twice the energy it receives from the Sun. Somewhere deep within its layers, heat is escaping, heat left over from its formation or produced by slow gravitational contraction. That hidden furnace stirs the lower atmosphere, driving convection that rises through the methane haze like bubbles in a boiling cauldron. When those rising plumes meet frigid upper layers, they unleash jet streams that whip around the planet with unstoppable force. Voyager's infrared spectrometer detected these temperature gradients, warmer equatorial zones, colder poles, revealing a dynamic circulation system unseen anywhere else. Neptune's atmosphere is organized into alternating bands of eastward and westward winds, forming a vast planetary jet pattern. The equator flows westward, while mid-latitudes stream eastward, creating shearing zones where storms are born. The Great Dark Spot formed within one of these shear regions, sustained by the energy difference between opposing currents. Scientists still debate why Neptune's winds reached such incredible speeds. Some models suggest that the planet's deep layers, composed of hydrogen, helium, and superheated water-ammonia mixtures, form a frictionless boundary that allows winds to glide over the interior without losing energy. Others propose that atmospheric methane acts as a thermal regulator, trapping heat and amplifying circulation. Whatever the cause, Neptune's atmosphere is a perfect engine of motion, converting small amounts of internal heat into colossal kinetic energy. Voyager's data also revealed that the Great Dark Spot wasn't alone. A smaller vortex, dubbed D2, spun in the opposite hemisphere, accompanied by a bright, fast-moving feature nicknamed Scooter, a streak of high clouds racing around the equator in less than 16 hours. These phenomena hinted that Neptune's weather operates on timescales utterly unlike Jupiter's, transient, evolving, almost alive. Where Jupiter's red spot has endured for centuries, Neptune's storms form and vanish in years, reshaping the planet's face with every season. Indeed, the Great Dark Spot itself proved ephemeral. When the Hubble Space Telescope later observed Neptune in 1994, the storm was gone, dissolved perhaps by shifting wind currents. In its place, new dark vortices appeared in the northern hemisphere, one of them nearly identical in size and shape. Neptune's storms, it seems, are migratory phenomena, born in the turbulent mid-latitudes, drifting across the planet before disintegrating. Each is an echo of the deep convection that drives the atmosphere, a heartbeat of the planet's hidden energy. The clouds around these storms are equally mesmerizing. Voyager's cameras captured high-altitude methane ice clouds casting shadows on the layers below, the first time such shadows had ever been seen on another planet. These clouds formed where vertical convection pushed vapor upward into colder regions, freezing it into bright crystals. The result was a three-dimensional atmosphere, with towering storm systems reaching hundreds of kilometers above the surrounding haze. Under Neptune's dim sunlight, these clouds glowed pale blue and white, forming luminous ribbons that coiled around the dark vortices like whirlpools of frost. Even more astonishing were the supersonic jet streams that encircled the planet. Near 70° south latitude, Voyager detected winds exceeding Mach 2 relative to Neptune's rotation, faster than the speed of sound in that frigid atmosphere. These jets whipped around the planet every 16 hours, generating immense shear forces that sculpted the clouds into intricate bands and spirals. At the poles, the winds twisted into giant gyres, forming polar vortices that may extend deep into the interior. Unlike Jupiter or Saturn, Neptune's polar regions are thermally inverted, with warmer air above colder layers, a sign of heat rising from within. For planetary scientists, Neptune became the ultimate paradox. The farthest planet, yet one of the most energetic. The coldest, yet driven by unseen heat. Its interior remains a mystery. Beneath the blue clouds lies a mantle of exotic ices, water, ammonia, and methane compressed into supraeonic forms where hydrogen ions drift through crystalline oxygen lattices. Deeper still, a rocky core glows at thousands of degrees. Between these layers, electrical currents generate a tilted, off-center magnetic field, much like Uranus's, twisting and snapping with every rotation. The combination of magnetic chaos and atmospheric violence makes Neptune a world of extremes, a laboratory for physics that Earth can barely imagine. The radiation environment around Neptune also astonished scientists. Voyager detected bursts of radio emissions from the magnetosphere, as well as auroras flickering near the poles. Though faint compared to Jupiter's, these auroras proved that the solar wind still touches even the farthest planets. The magnetosphere's corkscrew tail stretches millions of kilometers into space, interacting with the solar wind in a complex ballet of magnetic reconnection and plasma waves. The same forces that power the auroras may also inject energy into the atmosphere, feeding the winds that roar endlessly across the blue sphere. Neptune's storms, transient though they are, remind us that planets are not static or frozen relics. They are living systems, evolving and changing even in the deep cold. Hubble, Keck, and the James Webb Space Telescope have since tracked new dark spots appearing and fading across Neptune's face. One such storm, discovered in 2018, drifted northward before inexplicably reversing course, the first such reversal ever observed. The cause remains unknown. Neptune's meteorology operates by rules that remain elusive, shaped by pressures and temperatures we can barely model. In recent years, scientists have speculated that Neptune's internal heat may fluctuate over decades or centuries, driving cycles of atmospheric activity. The planet's slow seasons, each lasting more than 40 Earth years, could also play a role, altering the balance between sunlight and internal warmth. Yet even these vast rhythms cannot fully explain Neptune's excess of energy. The source of its power remains one of planetary science's great mysteries, a cosmic paradox that challenges our understanding of how worlds live and age. From a distance of billions of kilometers, Neptune glows faintly in blue light, its storms hidden beneath the methane veil. But those fleeting images from Voyager 2 endure, snapshots of a world at once alien and familiar, violent yet graceful. They remind us that nature's dynamism knows no boundaries, that even where sunlight fades to starlight, the pulse of motion continues. If Jupiter is the solar system's thunder, Neptune is its whispering hurricane, unseen, unheard, yet full of energy that refuses to die. Its storms are not simply weather, but expressions of a planet's soul, vast, cold tempests powered by an inner fire that has burned for billions of years. And so, at the outer rim of sunlight, Neptune stands as both question and answer, proof that the solar system's vitality does not end with distance. It continues endlessly in the roar of invisible winds and the dance of blue storms on a planet that defies the darkness. When Voyager 2 left Neptune behind in 1989, it aimed its cameras one final time toward a small, pale sphere orbiting in defiance of all planetary order. That sphere was Triton, Neptune's largest moon, a world as haunting as it was mysterious. To planetary scientists, Triton represented not just a satellite, but a paradox, an active, geologically complex body circling the coldest planet in the solar system. In a realm where sunlight is little more than a whisper, Triton was alive. At first glance, Voyager's images of Triton looked deceptively calm, a pale, pinkish surface with smooth plains and delicate ridges, so cold that nitrogen and methane lay frozen across its crust. Yet beneath that serenity lay motion. The spacecraft revealed a world younger and stranger than expected, a surface with almost no impact craters, suggesting that it had been reshaped in geologically recent time. The landscape was fractured, layered, and streaked by what appeared to be flows of volatile ice. Scientists had expected a frozen relic. What they found instead was a world that was impossibly active. Triton is about 2,700 kilometers in diameter, slightly smaller than Earth's moon. But its orbit immediately marks it as extraordinary. Unlike every large moon in the solar system, it travels backward, in a retrograde orbit opposite to Neptune's rotation. Such a path could not have formed naturally around the planet. Instead, it must have been captured, a wanderer from the Kuiper belt, drawn in by Neptune's gravity billions of years ago. That capture was likely catastrophic. The gravitational disruption may have torn apart Neptune's original moons and unleashed tides so enormous they melted Triton's interior, turning ice to ocean and forging the strange, fractured world Voyager found. The surface Voyager revealed was unlike any seen before. Instead of cratered highlands or volcanic plains, Triton displayed vast, smooth expanses crisscrossed by dark streaks and irregular pits. The southern hemisphere was dominated by a bright polar cap of frozen nitrogen, laced with methane and carbon monoxide ices. Along its edges, Voyager captured something no one had expected to see: geysers erupting from the surface, shooting dark plumes of gas and dust 8 kilometers into the thin atmosphere. These geysers drifted downwind, leaving dark trails hundreds of kilometers long. It was the first confirmed case of cryovolcanism, cold volcanism, in the outer solar system. Instead of molten rock, Triton's volcanoes erupted liquid nitrogen and volatile gases driven by the faint warmth of sunlight. The surface was so cold, about 235 degrees, that sunlight penetrating the thin ice crust could heat subsurface layers just enough to create pockets of gas. When the pressure grew too great, these pockets burst through weak spots, blasting plumes into space. The phenomenon was subtle but spectacular, proof that even in the most frigid regions, the forces of geology and thermodynamics still move. Voyager's spectrometers detected a tenuous atmosphere composed mostly of nitrogen with traces of methane. It was barely 1/70,000th as thick as Earth's, yet thick enough to support hazes and frosts that migrate with the seasons. As Triton's southern hemisphere basked in sunlight, the polar cap sublimated, frozen nitrogen turning to gas, which drifted around the globe and refroze in darkness. This constant exchange gives Triton a living surface, one that breathes with the rhythm of its 165-year orbit around the Sun. The patterns on its surface tell stories of these cycles. Voyager saw plains etched with cantaloupe terrain, a texture of rounded depressions, unlike anything on any other world. Some areas bore signs of ancient flows, perhaps of ammonia-water mixtures that once welled up from beneath. Others displayed fractures stretching for hundreds of kilometers, evidence of tidal stresses from Neptune's immense gravity. The moon's density and heat balance suggest that its interior once contained, and may still contain, a subsurface ocean of liquid water mixed with ammonia, a distant echo of the hidden seas beneath Europa or Enceladus. If Triton does hold such an ocean, it would make it one of the most remote potential habitats for life in the solar system. Though sunlight there is weak, the tidal flexing caused by Neptune's pull could provide steady heat, maintaining liquid pockets beneath the ice. Chemical energy from rock-water interactions, similar to hydrothermal vents on Earth, might fuel a slow subsurface biosphere. No spacecraft has yet confirmed this, but the idea endures that beneath Triton's frozen shell may lie warmth and chemistry, an improbable cradle of persistence at the edge of space. The mystery of Triton's capture deepens its allure. Models suggest it was once part of a binary system, two bodies orbiting each other in the early Kuiper belt. When the pair wandered too close to Neptune, one was ejected, while the other was seized. The violent capture may have destabilized Neptune's primordial moon system, scattering smaller satellites and leaving Triton as the dominant survivor. The energy released would have melted its interior, setting off an era of intense geological activity that resurfaced the moon and left it smooth and youthful today. Over time, Triton's orbit evolved into its current retrograde path, now circling Neptune every 5.9 Earth days at a distance of 354,000 kilometers. The orbit is slowly decaying. In perhaps 100 million years, tidal forces will draw Triton inexorably inward, tearing it apart and transforming it into a ring system, a final act of cosmic recycling. The serene face Voyager saw will one day disintegrate into dust and debris, circling the planet like Saturn's rings, a fitting fate for a captured wanderer. Triton's thin atmosphere and nitrogen frost have continued to change since Voyager's flyby. In the 1990s and 2000s, Earth-based telescopes detected a warming trend, perhaps seasonal, perhaps global, causing the polar ice to recede and atmospheric pressure to double. The cause remains unclear. Subtle variations in solar energy, volatile transport, or long-term climate cycles may all play a part. Even in its isolation, Triton remains a world in flux, a living experiment in planetary climate far beyond the sun's reach. The fascination with Triton has only grown with time. In many ways, it serves as a bridge between worlds, a captured Kuiper belt object orbiting a planet, sharing traits with Pluto, which would later be visited by New Horizons in 2015. Both bodies are rich in nitrogen and methane ice, both bear smooth plains and evidence of internal activity, and both likely share a common origin in the early solar system's outer debris disk. Studying Triton, then, offers a glimpse into the frozen frontier from which comets and dwarf planets emerge, the distant realm where the solar system was born. For this reason, many scientists now view Triton as the next great target for exploration. NASA's proposed Triton mission, a concept for a 2030s launch, would send a spacecraft to fly past Neptune and study Triton up close, mapping its surface in detail, analyzing its plumes, and probing its magnetic environment for hints of a subsurface ocean. Triton would arrive around 2048, nearly 60 years after Voyager's visit, a second look at one of the most intriguing bodies in the solar system. In a broader sense, Triton challenges our assumptions about where geological activity and perhaps habitability can exist. It teaches that distance from the Sun is not destiny. Energy, chemistry, and change persist even in darkness, driven by internal forces and gravitational tides. Its nitrogen geysers are whispers of this truth, delicate, fleeting eruptions that tell of heat and pressure working invisibly beneath the ice. In them, we glimpse a world that should be silent, but is not, a frozen moon that still breathes. As Voyager 2's cameras turned away, the spacecraft captured one last image. Triton's crescent, glowing faintly in Neptune's reflected light, framed against the black of interstellar space. It was a poetic closing, the final planetary image of the Voyager mission, the last look back before the spacecraft began its eternal journey into the void. Triton hung there, pale and lonely, yet full of stories, the end of one voyage, the beginning of countless questions. For in that small, distant moon lies the essence of exploration itself, that even at the farthest frontier, the universe still surprises us. In the icy silence beyond Neptune, where sunlight fades to a dim blue shimmer, Triton endures, geologically alive, atmospherically restless, and scientifically profound. It remains a monument to the complexity of creation, a reminder that even the smallest, coldest worlds can hold secrets as vast as the cosmos itself.